In the microscopic world of atoms and particles, one fundamental rule dictates the structure, stability, and diversity of matter, the Pauli exclusion principle. Formulated by Wolfgang Pauli in 1925, this principle states that no two identical fermions, particles such as electrons, protons, or neutrons with half-integer spin, can occupy the same quantum state simultaneously. Though deceptively simple in statement, this rule governs the architecture of atoms, the behavior of matter under extreme conditions, and the very possibility of the universe as we know it. At the atomic scale, the Pauli exclusion principle explains why electrons occupy discrete energy levels or shells around the nucleus rather than collapsing into the lowest energy state. Each electron must have a unique combination of quantum numbers, ensuring that atoms maintain distinct structures and chemical properties. Without this principle, all electrons would fall into the lowest energy state, atoms would collapse, and chemistry as we know it would be impossible. The diversity of elements, the formation of molecules, and the complexity of biological systems all arise from this simple, yet profound, quantum rule. The Pauli exclusion principle extends far beyond electrons in atoms. In the dense cores of stars, it provides the pressure that opposes gravitational collapse. Degenerate fermions, such as electrons in white dwarfs or neutrons in neutron stars, resist being squeezed into the same state, generating a quantum pressure known as degeneracy pressure. This pressure counterbalances gravity, stabilizing stellar remnants against collapse. Without the Pauli exclusion principle, stars would not end their lives as stable white dwarfs or neutron stars, and black holes might form much more readily, drastically altering the evolution of galaxies. Fermions are the building blocks of matter, and the exclusion principle ensures that their interactions are orderly and structured. In condensed matter physics, it explains the behavior of metals, insulators, and semiconductors. The electronic properties of materials, conductivity, magnetism, and even superconductivity are all influenced by the arrangement of electrons constrained by this principle. By dictating which quantum states particles may occupy, the exclusion principle underlies the vast range of material behaviors that form the foundation of technology and modern life. The principle also reveals a deep symmetry in nature. It distinguishes fermions from bosons, the particles that do not obey the exclusion principle and can occupy identical states in unlimited numbers. This distinction underpins phenomena such as Bose-Einstein condensation, where bosons collectively occupy a single quantum state, contrasting sharply with the rigid structure imposed on fermions. The Pauli exclusion principle, therefore, not only defines the behavior of electrons, protons, and neutrons, but also provides a framework for understanding the diversity of quantum statistics and the types of particles that govern the universe. Under extreme conditions, the exclusion principle continues to demonstrate its power. In neutron stars, matter is compressed to densities trillions of times greater than ordinary matter, yet degeneracy pressure from neutrons, mandated by the Pauli principle, prevents complete collapse. This principle also plays a role in high-energy physics, where quark degeneracy influences the structure of exotic particles and phases of matter such as quark-gluon plasma or strange matter. The exclusion principle operates at all scales, linking the behavior of subatomic particles to the structure of stars and the cosmos. Contemplating the Pauli exclusion principle is to recognize the hidden order in the quantum world. It is an invisible law that imposes structure, enables stability, and shapes complexity, from the electrons in a single atom to the cores of the densest stars. Without it, matter would lack rigidity, diversity, and the rich chemistry that allows life and the universe as we know it to exist. It is a rulebook that governs the distribution of particles, ensuring that the universe is coherent, stable, and capable of evolution. In essence, the Pauli exclusion principle is nature's quantum rulebook. It defines the arrangement of fermions, sustains matter under immense pressures, shapes the periodic table, and creates the stability necessary for chemistry, biology, and astrophysics. By enforcing uniqueness at the quantum level, it underlies the structure, diversity, and resilience of the universe. Studying this principle reveals the profound simplicity and elegance of the rules governing reality, demonstrating that even at the tiniest scales, order, constraint, and balance are essential to the existence of everything we see, touch, and experience.